If a nuclear missile is launched today, you have minutes, not hours, not time to decide. That's why the United States is building a shield designed to act faster than any human ever could. A system that decides before anyone can react. A system that hits first in space. Buried beneath ice rockets wait in silence. Above the planet, 1,000 machines watch constantly. If this shield fails, there is no backup plan. And if it succeeds, war itself may change forever. Don't blink, what you're about to see is humanity's most extreme gamble. For decades, missile defense lived in the world of theory. Charts, simulations, concepts that looked impressive but were never truly tested at scale. Stopping a weapon traveling faster than 20,000 miles per hour has always sounded impossible. Yet today, the United States is attempting exactly that. A $175 billion system, a defense shield stretching across land, sea, and space. Not designed to protect a single city or military base, but an entire continent. This is the Golden Dome, and if it works, it could change global warfare forever. The threat it's designed to stop is brutally fast and unforgiving. Intercontinental ballistic missiles leave their launch sites and reach space in minutes. Once released, their warheads fall back toward Earth at hypersonic speed. There is no time to negotiate, no time to debate, only minutes to detect, track, decide, and intercept. The Golden Dome is built around one core idea: destroy the missile before it ever reaches its target. Not with nuclear explosions, not with massive blasts, but by hitting it directly in space using pure kinetic force, a bullet hitting another bullet at orbital velocity. To make that possible, the system is built in layers, each layer covering the weaknesses of the others. Ground-based sensors, interceptor missiles, and above all of it, a vast shield in orbit. The first layer begins in one of the most unforgiving environments on Earth, northern Alaska. Here, construction doesn't begin with concrete. It begins with understanding the ground itself. Permafrost, frozen solid for thousands of years, becomes unstable if heated or disturbed. Build incorrectly, and entire structures can shift or collapse. So engineers drill deep, more than 30 meters down, anchoring foundations into stable bedrock beneath the ice. Rising from this frozen landscape are new radar installations, massive, precise, and far more powerful than previous generations. Their job is constant surveillance. They scan the horizon and the edge of space, searching for the faintest heat signature of a missile launch. Tracking objects smaller than a car from thousands of kilometers away, these radars don't just see. They calculate trajectories. They predict impact points. They feed real-time data into a system that must act without hesitation. Nearby, the second component of the ground layer is being built: interceptor silos. Each silo is a reinforced shaft buried deep beneath the ice. Inside sits a 3-stage interceptor missile weighing nearly 20 tons, designed to launch within seconds of a command. The interceptor carries no explosive warhead. Instead, it deploys a kill vehicle in space. A compact, highly maneuverable projectile guided by onboard sensors and computers. Its mission is simple: find the warhead, hit it. At combined closing speeds exceeding 25,000 miles per hour, the collision releases enough energy to vaporize the target. No explosion, no debris cloud, just physics. Once installed, these interceptors wait silently beneath the ice. Dormant guardians, ready for a command that may never come. But even with the most advanced radars on Earth, there is a problem. Ground-based sensors can't see everything. The curvature of the planet creates blind spots. Terrain, distance, and angle all limit visibility. To close those gaps, the Golden Dome must extend into space. And this is where the project becomes truly unprecedented. Above Earth, a massive satellite constellation is being assembled. Not dozens, not hundreds, but roughly 1,000 satellites working together as a single system. Each satellite acts as an eye in orbit. Equipped with infrared sensors sensitive enough to detect missile launches from space, able to track warheads through the cold darkness above the atmosphere. Unlike traditional satellites, these are not built one at a time. They are mass-produced. The approach borrows from automotive manufacturing, standardized components, modular design, assembly line precision. Satellite frames move down production lines. Wiring harnesses are installed, sensors are mounted. Solar arrays are folded with extreme precision. Each satellite carries its own propulsion system, ion thrusters that allow it to maneuver, adjust position, and maintain its orbit. This mobility allows the constellation to constantly reorganize itself, filling gaps and replacing failed units. Before launch, every satellite is tested aggressively, shaken to simulate rocket vibration, frozen and baked to mimic the temperature extremes of space. Only units that survive the full process are cleared for flight. When ready, the satellites are stacked tightly inside rockets. Launched in batches, dozens at a time. Once deployed, they spread out across carefully calculated orbital planes. Some cover polar regions, others focus on mid-latitudes. Together they form a continuous web around the planet, but the satellites do more than observe. They communicate. Laser links connect satellite to satellite, passing data at the speed of light. Information flows instantly across the network, creating a single, unified picture of the battlefield. Missile detection from orbit is relayed to ground radars. Ground radars refine the tracking data. Command centers calculate intercept solutions. Interceptor missiles receive precise targeting instructions. All of this happens in seconds. Redundancy is built into every layer. If one radar fails, another takes over. If a satellite goes offline, neighboring units compensate. If a communication path is disrupted, alternate routes activate instantly. There is no single point of failure, because there cannot be. The scale of the operation is staggering. Components are built across multiple states. Satellites launched from different coasts. Interceptors transported thousands of miles to remote Arctic sites. Reusable rockets play a critical role. Boosters land, are refurbished, and fly again, reducing cost. Increasing launch tempo, week after week, month after month, launch after launch. Slowly, the shield takes shape. In orbit, satellites unfold their solar panels and power up. They establish laser links. They begin their gradual climb to operational altitude using ion propulsion, a journey that takes months. And then, once positioned, they never stop moving. Circling Earth every 90 minutes, watching, tracking, waiting. When fully deployed, the Golden Dome represents a fundamental shift. Defense no longer starts at the border, it starts in space. The goal is deterrence through certainty. If an attack cannot succeed, it becomes less likely to happen. Whether the system will ever be tested in real combat is unknown. And that uncertainty is exactly the point. Because the true success of the Golden Dome would be silence. No launches detected, no intercepts required. A shield that exists so powerfully, it never needs to be used. For now, it remains one of the most ambitious engineering projects ever attempted. A fusion of manufacturing, software, aerospace, and physics, built across ice fields, oceans, factories, and orbit itself. A $175 billion question hanging above the planet. Can humanity build a shield fast enough, smart enough, and resilient enough to stop the deadliest weapons ever created? The Golden Dome is the answer the United States is betting on.